Find the values of h for which the vectors are linearly dependent. So let's quickly keep in mind here that an index set of vectors is linearly dependent if the vector equation has a non-trivial solution. So we want to find the value or values of h such that the vector equation defined by these three vectors, so we'll say x sub 1 times vector v sub 1 plus x sub 2 times vector v sub 2 plus x sub 3 times vector v sub 3 equals the 0 vector, has a non-trivial solution, or the existence of a free variable. So, to get us started, in order to find these values of h, we need to put this vector equation into the equivalent augmented matrix and row reduce. So we are going to row reduce the augmented matrix defined by the column vectors v sub 1, v sub 2, v sub 3, and we're augmenting this with the 0 vector to find h. So here we go. We have our first column vector, 2, negative 2, 4. Our second column vector is 4, negative 6, 7. And last but not least, our third column vector is negative 3, 3, h. And since we're augmenting this with the 0 vector, you can include that 0 vector, but we don't have to. Okie dokie. So, starting with our first pivot position, we want to use this to eliminate the entries below it. So, to eliminate the negative 2 in the second row, we simply need to take the first row and add it to the second row to attain the new and reduced second row. And then, to eliminate the 4 in the third row, we'll do minus 2 times the first row plus the third row to attain that new and reduced third row. So here we go. Our first row remains as it is. We have 2, 4, negative 3. And our first reduction, we have 2 minus 2 to give us 0. We have 4 minus 6, which leaves us with negative 2. And we have 3, or minus 3 plus 3, which leaves us with 0. And moving on to the third row, we have negative 4 plus 4, which gives us 0. We have negative 8 plus 7, which leaves us with a minus 1. And last but not least, we have positive 6 plus h, which leaves us with 6 plus h, or h plus 6, whichever you prefer. Beautiful. So our first column vector is all set, and we can move to the second pivot position. So here we want to use this pivot to eliminate the entry below it. So to do this, we can scale the second row by a factor of negative 1/2, and then add this to the third row to attain the new and reduced third row. So this is going to leave us with the equivalent matrix. So our first two rows remain as they are. We have 2, 4, negative 3, 0, negative 2, 0. And then we have, well, 0 plus 0 leaves us with 0. We'll have positive 1 minus 1, which leaves us with 0. And then last but not least, we have 0 plus h plus 6, which leaves us with h plus 6. So looking at this new row equivalent matrix, we have attained echelon form. Now we want to be careful. We have a term in each one of the columns for our basic variables. But our goal here is to find h such that the vectors are linearly dependent. So let's keep in mind that this vector equation, as we defined above, is going to have a non-trivial solution if a free variable exists. So the vector equation has a non-trivial solution if at least one free variable exists. So we want to solve for h such that x sub 3 is a free variable. So we want x sub 3 to be free. So in order for this to be free, we want h plus 6 to equal 0. So solving for h, we see that if h is equal to negative 6, then x sub 3 will be free. Woohoo! And we're ready to make our final conclusion. We can say that when h is equal to negative 6, x sub 3 is free, and the vector equation will therefore have a non-trivial solution. And so, by definition, if the vector equation has a non-trivial solution, the set of vectors v sub 1, v sub 2, v sub 3, this indexed set of vectors is linearly dependent. And so this is our beautiful final answer. When h is equal to negative 6, x sub 3 is a free variable, meaning that the corresponding vector equation has a non-trivial solution, and the set of vectors is linearly dependent.